So our displacement W is represented as a function of x and a function of the variable time. So a function of position and a function of time is represented as the product of those two functions. That's the essence of separation of variables. It actually works pretty good for many types of continuous systems. All right, so upon doing that, we can substitute that in, and hopefully you remember when we worked on the board over here, what did we do? We showed you when you take the derivative of W with respect to variable X, what do you get? What do you have to use to take that derivative? Product rule, right? Yeah. Anybody remember me doing that on the board? No. All right. All right, good. And then to take the second derivative of that with respect to X, you have to use what? The product rule. All right. When you use the product rule to take the derivative of W with respect to X, this guy tends to disappear. It goes to zero because it doesn't depend on X. So you end up with second derivative of W with respect to X. I use the primes in my notes. You're welcome to do that in the exam or your problems. Is essentially just X double prime times T. All right, that's what we get when we use the product rule twice. Take the second derivative of W with respect to X, we get this. Similarly, when we take the first derivative of W with respect to time, we have to use the product rule. Take it again, use the product rule again, we get W. Double dot, second derivative of W with respect to time, we get the function X times the second derivative of the function T with respect to time. All right, important step. All right, so I wrote it. I know it, so I just wrote it. And I've gone through the product rule enough times that I know what I'm doing there. Just write that out, substituting in. And now the essence of separation of variables is to move all the spatial dependent terms to one side. I always tend to put them on the left side of the equal sign. The time dependent terms on the right. And along with the time dependent functions, I always put the material properties. All right, so if there's a modulus or an elasticity, which there isn't, there's modulus, elasticity, and the density, they get shoved over to the side where the time dependent function. All right. Now at this point, we talked about this a little bit. We said, hey, if you take the derivative of this with respect to time, what do you get? Zero, and it doesn't depend on time. All right. Therefore, it has to equal a constant. One of the first things you felt one. I didn't go through and derive that this is a negative constant, but I did talk about it. It's a positive constant, zero, which is also a constant. You get a trivial solution. The only time you don't get a trivial solution for this problem is if we have a negative constant. Furthermore, I define it as a negative constant squared because I don't want to have to deal with square roots. I'm writing square roots in my equations down here. So I have always defined that as some negative value squared. And that gets sigma. Probably just your book use. There's no sense in making different variables than what the book sheet. Many of you are using that, I'm sure, as well. All right. So from this equation, what do we get? Tell me what you get from this equation right here.
Well, you get a relationship.
Anybody? Well, we already have the equation motion up here, but yeah, you're right. We can get two equations. We get our second order ordinary differential equation, spatial dependent one, and the time dependent one. See how we use this to get this. Everybody see that?
Yes.
All right. So this is very important at this point because now to get our mode shapes are basically this function x. So we just need to figure out what this function is. In other words, we need to solve this equation using the boundary conditions which are given, and we have our function x. Over here, this is the time-dependent equation. We can solve for t, and you have the temporal component of this. At the end of the day, we really don't need to solve for that. We need the initial conditions, which makes it a much more involved problem because we need to know what that bar is doing at every position x is equal 0 with respect to the space displacement velocity, and that is a function type boundary condition or a function type initial condition, not just a number. So solving for t actually is pretty involved, but looking at this equation and recognizing the coefficient out here is 1, then this coefficient has to be what? Natural frequency squared. All right, so notice I make a little note there right away because I know that to be true, and I don't want, forget about that, so I'm going to make a little note of that right there. All right, so moving forward, we always solve for the spatial dependent function first. And at this point, I write this equation out, straight out from this, because I know that's the solution. And how do I know that?
Yeah, sure.
I attended the first lecture of this class.
Yeah, it's your general.
Y'all hear me
Yes.
all right? Please mic up. Anybody having a problem hearing me? I forgot the mic. My voice is like going, so I'll mic up.
Yeah, conditions. General equation. And here, let's go here.
All right. Better? All right, so this equation I know is the solution for a second order ordinary differential equation. All right? For x is uppercase, and you have to be a little bit careful here. I tried to be careful. This uppercase is a function of the variable of the lowercase variable x. Right? So you got to make sure you see that if you're copying.
I did a better job here.
So this function x is equal to a sine sigma, a constant sigma here, times the variable x plus b cosine sigma. All right, so by applying the two boundary conditions, I always tend to apply the first one first. I guess you don't have to go in any particular order, but I did. I need the derivative of this with respect to x. Y'all tell me what that is. Derivative of this, sine and cosine, pull out the sigma here. And the derivative of the cosine, it's going to be negative sine. Again, you have to pull out that sigma constant. All right, evaluating x, that's 0 at the variable value of 0. So when cosine of 0 is what? 1. Sine of 0 is 0. So what we're left with is 0 is equal to a sigma minus 0 or a 0. This immediately tells us what? This immediately tells us that our mode shapes are basically cosine sigma x. See that? Let's see that. Everybody remembers that x, our mode shapes for continuous systems are functions, not vectors, right? That's a nice easy question to ask. Right? Since we know we're defining x at we're defining w as slicing in every infinitesimal slice of x, mode shape vector would have to be how big? That's another good question. How big would that have to be? We wanted to describe a mode shape of a continuous system with a vector as a function. Infinite by 1. Yeah, it's pretty big. That's why we use functions. All right. So at this point, we can go on to the second boundary condition. The displacement will be 0. The function x will be 0 when the variable x is equal to L. So this leads to cosine. I think I might have left a little s off here. Sorry about that. This is cosine sigma L. And what is the cosine of anything 0? So what value of sigma L satisfy this? Cosine sigma L is 0. Pi over 2 radians. 3 pi over 2 radians, 5 pi over 2 radians, 7 pi over 2. Do y'all see that? I can draw it out as well. Think about it. Cosine sigma L versus sigma L. Wherever cosine sigma L is 0, that's the solution to this equation. The O of S in here, of course. I wrote it out in this form. I don't remember why. I just wrote it out. If you decide to do it that way, the way that I just verbally said, pi over 2, 3 pi over 2, 5 pi over 2, dot, dot, dot. Just write out at least the first 3. I'll just write the first one. All right? Any questions on that? All right? Go ahead. All right. Good question. All right. So what I'd like you all to do is pull out a piece of paper and a pen and draw cosine of sigma L versus sigma L. That's the kind of question that I fully expect I want to ask. So thank you for asking. So draw a plot on the horizontal axis. I mean, you can use. I'd like to use sigma L. On the x-axis or the horizontal axis, sigma L. On the vertical axis, cosine sigma L. All right. What are you going to draw? You're going to draw a cosine curve, right? Everybody got it? You need me to do it too? Very good. Very good. I'll draw it because I want to make sure you guys see the way on this. All right, so I have this equation. Cosine of sigma L is equal to 0. That's an equation. You might not think of an equation. Anytime you have an equation. All right. Well, what values is that equal? What values is that true? Values of sigma L make that true. We have cosine 0 to a bunch of values, right? So we want to figure out what value is sigma L. Satisfy the condition. Cosine equals 0. We see all right?
Yeah, it's 2 odd numbers.
Yes or no? Yeah. All right. Okay, so here's my cosine. Okay, and plus 1 and minus 1. Right here, that corresponds to pi over 2, 3 pi over 2, 5 pi over 2, etc. 7 pi over 2. You got the idea, right? So cosine of sigma L equals 0 is true whenever sigma L is pi over 2, 3 pi over 2, 5 pi over 2, dot, dot, dot. Now, if you see that that's equal to this, which is, you write this. Right? Sigma L. The question that I had is how do we know when to use this versus pi over 2? Where do you think so that we got a different solution for this in the notes, right? Why was it different? Remember? Because we were looking at the equation was different. The sign of sigma L equals 0. Sign of sigma L equals 0. We have different terms. We have different values of sigma L to satisfy. Does that make sense? Good. Well, I make it more difficult. No, it is. But, I mean, at the end of the day, it's unclear, which honestly, you guys, yeah, that's when you think a lot of folks have things in their head. A lot of people do, but a lot of people, if they don't remember something, will write it out. We think if there's any chance of loss of life or property or anything like that as an engineer, I was absolutely 100% sure what a problem like this even is, something as simple as this, I draw it out and I convince myself that it's true before I went further. Right? And you know, designing products and building things, using engineering tools, you should do the same. Right? In this case, we have a zero value of pi, 2 pi, 3 pi, 4 pi. In this case, sigma L, value of sigma L is at 5 times sigma L equals 0. All right, so to answer your question, yeah, sure. Yeah, it's complicated. Maybe you, all right? And then, of course, these are just a couple simple examples. I mean, we're not going to really get into anything much more complicated. But you could end up with five conditions of a problem, not really the problem, especially if it's more involved in science. So, cosine. You're solving the same way. It's the root solver, all it is. All right. So, the solution is minor boundary conditions. Here we can solve for sigma n. So write that out. I put a little box around it. I'm not going to, I didn't in this case feel like plugging it in my expression for omega n. So omega n squared is this. Taking the square root of that gives me my natural frequencies. And then plugging in this into what's left of x, I already said that a is 0, so just use cosine. We have a motion. Now I did keep this subscript n here and here and here to indicate that there's an infinite number. There's an infinite number. Everybody see that? It's another little add-on I can put to this problem. You guys think of a nice little add-on I can put to this problem? What's the third mode shape and the third active frequency? Right? How would you determine that? N equals 3. Okay. That's it. Everybody see that? Or I could ask for the 10,000ths. That should be better. Like this. Right? 10,000ths mode, please. And that's your frequency. Any questions on what I just said? Yes.
So,
Leave what?
for the constant term from the load shape.
All right. So does this even matter? Yeah, honestly, I usually leave it off. I don't know why it's there. You can leave it on or take it off. You can put 10 there, you can put 100 there, you can put 0.01 there. Put -3 if you want. It doesn't matter. It's still correct. All right, because it's mode shape. The mode shape is about relative value of the function x with respect to the variable x. All right, good question. All right, anything else? Now, I've already told you all that I would ask you this question. Why would I ask this question? That's a big question. Is why would I always ask this question? I ask this question because I've had too many adults who've done like years of research, not knowing this, in my office with tears in their eyes, saying, "Oh my dad is garbage." The answer was yes. You have to do everything. PhD or whatever that you're working on. All right. So define aliasing and list the key requirements. That's 30%. Misrepresentation of a high frequency prologue. Right? Way we avoid it, low pass filter. I don't state it here, but it's an analog filter. You can ask me that too, but I won't. It's an analog and it operates on the analog signal before we do any ADD. Digital. Before ADD conversion. Right? Honestly, I think we should remember that the whole thing, not just AA. All right, we're going to go to that. 4 analog. And we sample it 2.56 times the maximum frequency. Right? No excuse to miss that problem. All right. What does that mean? Right, so when you see a question like that, the first thing you might want to say to yourself is, what's the purpose of a window? Right? Right? Remember, one of the problems with signal processing, if you're interested in extracting frequency content from a measurement, so remember we take a measurement with an accelerometer, for example, or anything for that matter. We're interested in the frequency content, which is vibrations. Do you think we're interested in the frequency content of signals with a measure? Yeah. Yes. Yeah, absolutely. It tells us things like, you've got a problem here, there, also tells us what the frequencies are. Frequency content is important. Sometimes what happens, or most often what happens, is that when we apply the Fourier transform, and I don't know if you all remember this or not, but what does the Fourier transform assume? What does the Fourier transform assume?
The series of sinusoidals.
It assumes that whatever your time record is, it continues exactly in the same form, going in the negative direction with respect to time and the positive direction with respect to time. So whatever you give it, whatever your time record, whatever your measurement is in time, it says, hey, this is what we got. This repeats exactly as we got it in both directions in time. All right? So what happens when you look at your notes and I construct it, you'll see it again. It introduces discontinuities at t equals 0 and t at the end of your time record measurement. Those discontinuities tend to smear the frequencies. I personally would wish that this would call it smearing the frequency, but they call it leakage, which honestly I guess is fine, but I'm not going to change it either use. So I write reduces leakage, and then I put in parentheses because some students might write, reduces the sparing frequency. So I put that in there so if he is grading this problem, he or she will know that that's acceptable. All right? Any questions on windowing? I agree with this absolutely. I agree with this security. How many of you would get this right if I asked that in the test? How many would get it wrong or have no idea what I'm talking about? All right. You cannot believe how poorly received this question was this last semester. I couldn't believe it. I couldn't believe it. Honestly, let's ask again, how many would get this right? There was one of you guys who left the answer. Very good. You let her get there right. You can't even have a conversation for 2 seconds. There was good school without knowing acronyms, which seems like college for that matter. Anyway, so FFT stands for fast Fourier transform. Again, this to me, this problem was a gift. It was meant to be a gift. It wasn't wasn't a gift at all. It was, oh my God, what's that going to be? It's such a hard question. So that's the response that I got from many students. And I don't, other than to shake my head and disbelief, I don't know what to do about that. But that's, so I'm happy to see that you guys would get it right. All right, fast Fourier transform, that's what that stands for.
What kind of answers did you get?
I don't remember. They were funny enough. A better question, in my opinion, what you didn't ask is, what does FFT stand for and how is it different from DFT? You know the answer to that? That's a big senior level question there, and actually it's college boy level or girl level question, in my opinion. That's the kind of question that I should be asking, not what's that? All right. Anybody answer that question? What is FFT and how is it different from DFT or just straight Fourier transform? Very good.
One
It has to be hard to do. Why? It's an efficient. It's a very efficient algorithm for calculating Fourier transform. You just do straight Fourier transform, also known as the discrete Fourier transform. It's very inefficient. It's very time consuming, especially with computational power that we had 20, 30 years ago when we were doing stuff when it was first coming out. Nowadays, probably as necessary as it was then. Okay, here's another question. All right, get it all in there. I think this is actually kind of an important thing to remember. All right, and I don't really think it's that tough, but list the 4 steps in FEA pre-processing. All right, so pre-processing is what? Define your geometry. What else? Define material properties. Define your boundary conditions. And mesh. Now, in addition, I don't, usually we'll also define your element type. That's not really required in the software we use. It's default. It has grade limits set element. Some folks won't like the word define geometry. They'll say build your solid model. That's fine. It's the same thing. That's it. All right. I'm feeling that based on the last question that you'd all probably get this right too. Right? Any questions? All right. So this one is one that we talked about. And I don't know. Again, I'm going to believe up. Nice to use it. All right. So we talked about frequency response measurements and using those measurements to extract mode shapes. And I've stepped through a couple. So this question is estimate the third mode shape, the following structure with the following frequency response data. All right, so up at the top, you see the structure, same one as in the note, 3 points. Everything's the same. You got an accelerometer, you got a hammer hitting at point 1. And then you've got these 6 plots. Any idea what these things are?
It's magnitude response and coherence.
So right here, this is the magnitude of the frequency response when the accelerometer and the hammer are both at 1. This is the corresponding phase. If we were to move the accelerometer or the hammer, doesn't matter which one, move either one until point 2, keep the other one at point 1, this is the magnitude we get, this is the phase we get. We moved either the hammer or the accelerometer to point 3, kept the what was, let's just keep the hammer at 1, move the accelerometer to 3. We get this for magnitude, this for a phase response. All right? So, a couple of things. If we look at just the magnitude, what does that tell us? What does the magnitude plots tell us? 3 peaks, they show up in all 3 measurements, right? Ignore the phase for a minute. So the 3 peaks, they all show up in all 3 measurements. We're asking for the third mode shape. So if you're going to extract that just from the data, and I don't give you any equations or anything like that, and I use the word estimate, I'm expecting you to just look at that third mode shape. So can you tell me what frequency that third mode shape is occurring at?
Well, it's going to be,
See, first mode shape's 10, second mode shape's 20 radians per second, third mode shape's 30. So notice, I circle 30, just to make it clear. If someone's reading my work, I want to make sure I know what 3 means. That's the third mode shape. And I draw, you can barely see it, but I draw a vertical line, and then I put a mark, plus sign at the peak. All right, then I draw a horizontal line over for each one of these peaks. 0.15, 0.13, 0.7. See that? What is that information? Maybe tell me what that information is.
Y value.
Think of it like this.
That's your
We keep the hammer at location 1. The only thing we can do is move the accelerometer from 1, 2 to 3. You get this 1, 2, 3. The only thing that changes is the magnitude at that frequency as we move the accelerometer. That's basically the mode shape, and that's the number of mode shape. Everybody see that? So my mode shape is literally just 0.15, 0.13, 0.7, approximately. Okay? Well, we're not done yet, because we haven't looked at what? Phase. We don't know if they're all moving.
We don't know the sign.
Interesting.
So we come over here and we look at the phase. Again, which frequency are we looking at? All right, so do I have any business at all writing anything down about what's happening at 10, radians per second at 20? No. All right, so I go ahead and draw a vertical line here at 30, and then I come over here and look at my phase. Minus 90, plus 90, minus 90. Notice they're not exact. Why are they not exact? Exactly plus or minus 90. Maybe we don't have perfectly all nodes. Maybe the damping's not perfectly proportional to the structure. Okay, close enough for what we're trying to do here. All right, so that gives us a relative sign. Basically, when at mode 3, 1 and 3, position 1 and position 3 are in phase, so they'll have the same sign. I picked minus, negative, and then the middle one's out of phase, so it's positive. So you could write negative 0.15 plus 0.13, negative 0.7 here, or you could change the signs, plus, minus, plus. Do it. That's it. Notice I used the graphs that were provided by marking them to indicate that I know what's going on. All right? And then I rewrote all the data, even though I have it all circled. I rewrote it down here, and then it's all summarized here, and then I labeled it. Notice, approximate. It's pretty close. If we were to go through a more formal approach, that went over the notes, we get something pretty close. All right? Be a little bit better, but honestly not that much. I can ask either way, or either way. All right? Now, what happens if you were grading me, which, let's just say that was the case, and this is the question, and I started drawing lines and extracting data at 10, 20, and 30, how would you grade? What would your instinct be? That I know what I'm doing? I have no idea what I'm doing. I have no idea, right? So that's why I think I ended up grading this problem, because so the point is just be very careful to read and understand third mode shape. What does that mean? It's what's happening at the third natural frequency. You have no business looking at anything else. There's only 6 data points that are useful. They're the 6 data points that correspond to curves when you're at the third frequency, which is the third peak, which is 30 degrees. All right? Any questions at all? You guys good? Yes.
We did a different way than
Yeah, so we did it more formal way in class. Now, I went through this informally. If you didn't get into that lecture, then, you know, we don't have to talk about it further. This is the problem from what we talked about. All right, we did this. So when I first showed you this data in the notes, before we showed you the formal approach, you did equations, you know, derived from the actual mass from the amper columns. That I said, hey, we don't need to do the go further than looking at this data. It's very intuitive, and honestly, it makes sense. All you're doing, you're hitting it in the same spot, and you're measuring it. In fact, think of this. Think of hitting it here and having 3 accelerometers with your 4-channel analyzer to that. And then you collect all this data at once. You're actually measuring motion here, here, and here all at once. You expect the motion to be at different points? Yeah, that's what motion is. So this will give you the relative magnitude thing. All right. Again, in my view, if you're actually listening, going up to the lecture, listening, not watching or using your phone computer, it's an easy problem. Me. And you should be. Any questions? All right, the last one is actually a homework problem. This is too small. Yeah, I'm just split it.
Yeah, it's too
I'll
small.
do my own split.
Split. You can go
I'll
have
do
these.
both ways, how's that? Let's do it this way first. And then we'll split it. Talk about it.
Here's the problem. That I did it like this.
All right.
It's this one.
This one's a little different than the one I showed you in class, but we talked about this one, remember? We did, we talked about it. We have one in the homework that's similar. Basically, 2 elements, and they're different lengths. All right. Determine the finite element model, which is basically another way of saying equation of motion. Figure out the equations of motions. Equations of motion. For a free bar, so I took away the boundary condition, or I took away any fixed constraints. It's free over the boundary. There's no boundary condition. It's just one constraint. For free bar with the following 3-node, 2-bar element max. So it's only bars is all we look at, bar element. Why? Element 1 has a length L over 4, so I did switch it up from what's in here. The one that's in your book, I think I gave it homework. One element is L over 3, and then the other one is 2 L over 3. This is a little different. Element 1 has a length L over 4. Element 2 has a length 3L over 4. All right, so here's our first element. Has nodes 1 and 2, so its nodal displacements are U1 and U2. Element 2 has nodes 2 and 3, its nodal displacements U2 and U3. The element stiffness and mass matrices for a bar element of length L are given here. All right, so if this is the stiffness matrix for an element of length L, what's the stiffness matrix for a bar element of length L over 4? You substitute in L over 4 for L. So I did. For an element of length over, substitute in L over 4. Now, while I was at it, I didn't really feel like writing this anymore than I had to. I went ahead and expanded it out to include U3, which it does not depend on, but I'm going to use this, the efficient way of determining my equation of motion that I showed you. So I go ahead and expand it out to include a final column and row of zeros. this is it. It's exactly this, with an extra row and column of zeros, and then I replaced L with L over 4. Do you follow that? I'm doing same thing here. So for my first element, which I'm calling 1, so I use a subscript 1. All right. Substitute in L over 4 for L. So what does this become? That becomes a 24. And I've had some extra zeros on the final row and column. Again, to include U3. Similarly, for element 2, its length is 3L over 4. So I substitute in 3L over 4 for L. So that's where this 3 and this 4 are coming from. And now I'm going to expand it out so that it includes nodal displacements. And so I've got a row and a column of zeros at the front end. All right, again, same thing for the mass matrix. Any questions at all about what we're doing right here at this point? Yes? Why did I put them where I put them? All right, that's fine. Good question. That's fair. All right, so let's back up a little bit here. All right. This is very clear what's coming from. KI is the I element synthesis matrix. All right. Where in the world did I get that from?
Problem.
Where did I get that from? What? Turns out, yeah. So it's basically, we basically derived this from the strain energy or potential energy law. You know what that was? The borrow the length, we call it D. It was 1 half. Strain energy law. All right. Now, truth be said, a bar element is how it has so many nodes. The bar element has so many nodes. So, I don't know, pick whatever value. I could use I and J, but I'm trying to get something easy. Well, let's just use 1. So let's just say the nodes for the element that we're looking at. Let's just look at one of these in this problem. So let's look at element 1. We'll put a 1 here, and we'll put 4 here. Okay? That's really that element. Elements. You guys all good? You see what I did? Do a 1, 4 in here, that represents elements. Now, really, where did that come from? I'm glad you have the question. All right? It came from the strain energy and potential energy from that element. All right? And since it only depends on those places G1 and G2, U in this case is really the most compact form to write that is like this.
That is potential energy, which is going to be 1/2 kx squared.
I'm just carrying that 48 without. Then I've got 1 minus 1 minus 1, 1 times U1, U2. All right? Okay, fellows at all going on? You guys recognize it at all? Any questions?
we were to multiply this out, which I can, I really don't want to. If I were to multiply this out, how many terms do we have? How many say 30? You say 10. You say 1. You say 3. Really? Oh, that's 3. 3 terms. So when we first derived the equation for the strain energy or potential energy for a bar element for the 3 terms, we call those. Okay, we went through, we applied the Grom's equation in class, right? Then we said, hey, let's look at this 3 element model. I said, when we, hey, by the way, when we look at the total energy, there's 3 elements, each strain energy element, strain energy for each element will have 3 terms. The total strain energy will have 9 terms. We're going to apply the Grom's equations to that. And obviously, they're not huge, but it's growing. Okay? So, by the way, I want to show you a different way to do this. So I did. I showed you. We can rewrite this strain energy instead of this 3 terms that depend on Q1 squared, Q squared. We can write it out in a matrix form. And when we do this, we're going to define an element stiffness matrix. All right? Good? Now, this is really what it is. But there's no reason in the world we can't expand it out and write it like this.
Oh, okay, this is where showing you the expansion. You see that right here too. Expand one right here.
All right, and all I did here is I rewrote the strain energy in terms of U1, U2, which is what it really depends on, and U3, which it doesn't depend on. All right? To do that, I had to really define U as not just the element nodal displacement vector. I had to redefine U as the system nodal displacement vector. Okay, so U is a little different here. So it's 3 by 1 instead of 2 by 1. All right? First change. All right? V1 and V1 are equal. So the only way they can be equal is for this matrix. Now it has to be 3 by 3 to these two zeros. And if you multiply that out, you get exactly the same. All right? So the question at this point is, why did I do this? Why did I do this?
Because you have to sum. You have to sum.
We're not interested in just the element energy. We're interested in system energy. We have to add them. We have to add, in this case, V1, V2. We have to add the strain energy. We have to add the kinetic energy. We have to add them up. And so that's the reason for rewriting the elements matrices, expanding them out. We call it expand them out in terms of all the nodal displacements and all the nodal velocities. All right? Good? Any questions? Does that help? All right. So that's all we did. So, really,
Like this one looks like.
this is basically the same
They're
thing.
literally adding these together. Oh,
From an energy point of view. Well, the only difference is this really is the element, this matrix, this is expanded out to include all the nodes in the system. All right? We're going to do that for element 2 as well, but element 2, there are basically subscripts. Element 2, got 3 here, got 3 here, got 2, 2, 2. It's a little tricky here, but I believe that I have it correct. Notice the first thing, when I write out my strain energy for the second element, I have to correct the line. But it really all depends on U2 and U3. All right? They follow? If I want to expand that out in terms of U1, U2, U3, then I have to add in U0. Probably helpful, right? So, that's why it should look like that. Okay. All right. Well, our test centers. Now we have K1 and K2. We can add those together, and then that's the point. Really, what we're doing, what you're doing is you're adding V1 and V2. But the stiffness matrix that results in the total strain energy is in fact the system stiffness matrix. And then it indirectly has applied design equations. It saves a tremendous amount of time, and it's very efficient. If you've done any sort of programming with arrays, which honestly, if you've done programming at any level, you do a program with arrays. You have I've already done so writing code that can add these up, but still, it's doing at a much bigger scale than what we're doing here. All right, so we did the same thing. So good question. We did the same thing for the mass. Here and here. And those came from similarly the kinetic energy. All right. And now what we do, we add those up, and those give us a total. Hold back a little on that. Gives us the system. All right, so no constraints if you want or U3, nothing really fixing this thing. Just add them up. And there's a little bit of a potential for an issue here. The coefficients are different. So when the lengths are the same, the elements are the same, no problem, but when they're different, you have to be careful. So if you look here, I use the words, for adding these up, I'm going to rewrite K1 like this, and rewrite M2 as this, so that the coefficients out in the front are the same. That we easily add them, right? Why am I doing that? Because I don't want to try doing all 3 by 3 or 9 elements in my head. Essential for making mistakes, especially when I'm under pressure. Test, that kind of stuff. So that's all I'm doing here. Is when you see this section right here, all I'm doing is I'm rewriting it. In this case, looks like it divided this by 3, so I multiplied everything in here by 3. Right? Got it? And then here, looks like I multiplied everything by 2, so I had to divide everything out here by 2. Now my coefficients match up for the stuff out in front of the matrices, so adding them up is easy. This is now my system mass matrix. We sidestepped or indirectly applied the Lagrange's equation. This is my system mass matrix. This is my system stiffness matrix. And all I have to do is to take that mass matrix, multiply that by my nodal acceleration vector. All 3 nodes are participating. And then I take my system stiffness matrix, multiply that by my nodal displacement vector, add those, set it equal to 0 because there's no forces acting on it. There's no forces acting on it. I got my equation of motion. Questions?
Now, let me tell you, what I've seen with this kind of a problem, students either just get it, no problem. They understand, when you ask a good question, they understand what's going on, and then they're like, well, even if I don't understand that, my brain works better, or as good as a computer when it comes to algorithms, and I can just figure out how to add this and figure it out. So where mistakes happen on this problem, I'll tell you straight out, is when they would go to add K1 and K2, because the coefficients are a little different, and I'll pull it down, they messed it up. And it's not a big deal, but it's knowing, you know how to do this, you make that kind of mistake, you lose it. So be careful. So again, adding K1 and K2, notice the coefficients are different out here. There's a 3 here, there's not one there. So that's why I rewrote K1. And then here, same thing, M1 and M2, they have different coefficients. So I rewrite M2 so it matches this. So I had to change the stuff inside, but that's no big deal. Now adding M1 and M2, K1 and K2, I get this. That's really the main area of issue with this kind of problem. The other area, sometimes students won't write this as a vector, or they'll forget this stuff. They'll forget the displacement vector or the acceleration vector, or they'll write it as a scalar or something silly. Just write it out, right? Write it out. Write this out as a vector, 3 by 1 short. All right? That way you get 100% here. All right? Any questions at all?
So I decided this freaking zeroed out. This problem.
All right. Any questions about this? Any questions about this? Yep. So the only thing that's really different, so here's questions and problems, and then that answer page that is going to the form is quick questions. 5 questions. So that's the last question for you. All right? Other questions? And there's nothing from previous or course of comes from all right. Anything else? All right, I'm supposed to be sleeping, right? Where are you? All right.
John, when it comes to the energy stuff, this in a weird way models like your basic spring potential and your kinetic energy. Because if you put these together, it's U squared, X squared. I didn't realize that until I'm talking to my tutor. Here?